Helicopter Flying Handbook 11.4 Helicopter Emergencies and Hazards. Understanding low G conditions is crucial for helicopter pilots. In aviation language, G refers to the acceleration due to gravity. When you're in level flight or on the ground, you're experiencing 1G. However, during maneuvers like tight, banked turns, you might feel more than 1G, high G conditions. On the flip side, in situations like a downward ride in an elevator, you're in low G conditions, experiencing a weightless feeling similar to the start of a downward elevator ride. Now, helicopters rely on positive G for their control responses. The cyclic is used to tilt the rotor disc, and at 1G, the rotor produces thrust equal to the aircraft's weight. This tilting provides the necessary moment to control the fuselage's pitch or roll. However, in low G conditions, thrust and control authority are significantly reduced, posing a challenge, especially for two-bladed helicopters. During low speeds, such as initiating a takeoff or recovering from vortex ring state, forward cyclic maneuvers are generally safe. But, be cautious with abrupt forward cyclic inputs, especially at higher speeds in a two-bladed helicopter. If the helicopter noses over during a pushover, it enters a low G condition, reducing thrust and control authority. This situation can lead to an uncontrolled roll, commonly induced by factors like tail rotor thrust or aerodynamics. A critical risk in low G conditions is mast bumping, where the rotor hub contacts the rotor mast due to excessive cyclic inputs. This phenomenon has been a cause of numerous fatal accidents. Turbulence, particularly severe downdrafts combined with high airspeed, can also lead to low G conditions and mast bumping. Helicopters typically handle turbulence better than light airplanes due to their rotor blades' smaller surface area. To avoid mast bumping accidents, pilots should steer clear of abrupt forward cyclic inputs in two-bladed helicopters. Recognizing the weightless feeling associated with low G is crucial for quick corrective action. Uncommanded right roll in helicopters with counterclockwise rotor rotation indicates imminent loss of control, requiring immediate corrective action. Recovering from a low G situation involves gently applying aft cyclic before correcting any roll. Pilots should also reduce power and use slower than normal cruise speeds when expecting or encountering turbulence. Higher rotor flapping angles in turbulence and increased airspeeds make helicopters more susceptible to low G conditions. Utilizing flight simulators for training on low G conditions and mast bumping recovery techniques is highly recommended. It's worth noting that multi-bladed rotors may experience a phenomenon similar to mast bumping, known as droop-stop pounding, but occurrences are less common due to their retained control authority at low G. Maintaining the right rotor RPM is paramount for helicopter operations. Similar to how airplanes have a minimum airspeed for flight, helicopters have a minimum rotor RPM for safe operation. This critical parameter is indicated on the helicopter's tachometer and detailed in the Rotorcraft Flight Manual or RFM. If the rotor RPM falls below the safe range, the helicopter is in a low RPM situation, which, if left unaddressed, can lead to rotor stall. Rotor stall is distinct from retreating blade stall, a phenomenon occurring at high forward speeds. Retreating blade stall causes vibration and control issues but doesn't compromise the rotor's ability to provide lift. On the other hand, rotor stall can happen at any airspeed, and it leads to a rapid loss of lift, resulting in a swift descent. Imagine rotor stall is akin to an airplane wing stall at low airspeeds. Airplanes rely on airspeed for proper wing airflow, while helicopters depend on rotor RPM. As airspeed decreases or rotor speed slows down, the angle of attack or AOA must increase to support the aircraft's weight. At a critical angle around 15 degrees, the airflow over the rotor blade may separate and stall, causing an abrupt loss of lift and an increase in drag. Recovering from a stall in an airplane involves lowering the nose and adding power. However, in a helicopter, the rotor stall introduces upward airflow through the rotor disc, resulting in an extremely high AOA. Even with full down collective, normal airflow cannot be restored. Rotor stall is asymmetrical. The retreating blade stalls first, causing it to descend, while the advancing blade climbs, leading to a rapid aft tilting of the rotor disc, often referred to as rotor, blowback, or flap back. As the helicopter descends, the upward flow of air on the tailboom tends to pitch the aircraft nose down. Combined with any aft cyclic input by the pilot attempting to level the aircraft, the rotor blades can blow back and contact the tailboom, potentially severing it. Loss of main rotor RPM also causes a significant reduction in tail rotor thrust, resulting in a loss of directional control. Notably, rotor stalls are unrecoverable. At low altitudes, a rotor stall will likely result in a damaging accident, while at higher altitudes, it can be fatal. Early recognition of the low rotor RPM condition and swift recovery are imperative. Low rotor RPM situations can occur during power-off and power-on operations. Power-off scenarios may arise from failure to promptly lower the collective after an engine failure or by raising the collective too high above the ground during auto-rotation. Power-on rotor stall accidents commonly occur when the engine is functioning correctly, but the pilot demands more power than available by overpitching, especially at higher density altitudes. Recognizing a low rotor RPM condition involves visual cues such as observing a decrease in the rotor RPM indicator, a change in torque leading to yaw, a decrease in engine noise, and increased vibration at higher speeds or in turns. Many helicopters are equipped with a low RPM warning system. Recovering from a low rotor RPM condition requires immediate action. The pilot must simultaneously lower the collective, increase throttle if available, and apply aft cyclic to maintain a level attitude. Additional aft cyclic may be used at higher airspeeds to aid in recovering lost RPM. Recovery must be practiced to become a conditioned reflex for the pilot. In the realm of helicopter operations, system malfunctions can be effectively managed by strictly adhering to the manufacturer's recommendations, operating limits, and following periodic maintenance and inspection routines. Many failures can be prevented through these practices. However, certain malfunctions may still occur, and the pilot's actions, along with the application of threat and error management, play a crucial role in averting emergencies. One common type of malfunction is an anti-torque system failure, which generally falls into two categories. The first involves a failure in the power drive part of the tail rotor disc, leading to a complete loss of anti-torque. This can result from issues like driveshaft failures, tail rotor gearbox failures, or a total loss of the tail rotor. The severity of the resulting spin depends on the power used and the airspeed. In such situations, reducing power to manage main rotor torque and employing autorotation techniques are key. If the failure occurs in forward flight with sufficient airspeed, the vertical stabilizer may provide some directional control. The second category of anti-torque system failure involves mechanical control failures, which prevent the pilot from controlling tail rotor thrust. This failure is usually caused by a stuck or broken control rod or cable. While autorotation is generally not required in such cases, pilots should always follow specific manufacturer procedures. Another scenario involves handling a helicopter with a stuck left pedal, typically experienced during takeoff or climb conditions. This results in left yaw when power is reduced. Contrary to autorotation, the recommended landing profile entails a normal to steep approach angle, arriving about 2 to 3 feet above the intended landing area. This steeper angle allows for a lower power setting during the approach, ensuring that the nose remains to the right. Upon reaching the intended touchdown area, the pilot smoothly increases the collective to align the nose with the landing direction. A slight forward cyclic input helps prevent the nose from continuing to the right. If the nose is turning left before landing, the pilot aims to complete the landing before the turn rate becomes excessive. In case the turn rate increases prematurely, adding power facilitates a go-around for another landing attempt. Throughout these scenarios, the consistent application of specific manufacturer procedures is paramount for effectively managing system malfunctions.